Yeah, so the way we generally draw the axis, so right now we're in 3 dimensions, which is um, relevant to our day-to-day life. And we draw the axis like this. We put the x over here, the y here, and the z over here. And we call this R3. So now we're in 3 dimensions, x, y, and z. And what they're telling you over here is you want to put the x over here and the y over here, and the z goes on top. So you don't really want to flip them. You don't want the y and x to be like this. It just makes the orientation easy, and this is how everyone does it. So yeah, try to keep the notation consistent. And so when you are in 3 dimensions, again, you have your x, your y, and your z. So you have 3 points. Instead of in 2 dimensions, when you just have x and y, we have our coordinate system looks something like AB. So now that we're in 3 dimensions, our coordinate system will have A, B, and C. And the A is the x coordinate, B is the y coordinate, and the C over here is your z coordinate. So over here, P is this point over here, and it has its A, B, and C. If you look at the projection of P onto the YZ plane, so that's this plane in the background right over here, then the x coordinate, you see the x coordinate, it's 0 over here. So the x coordinate of this point is 0. But the B and the C, well, this is your C coordinate and this is your B. So the C is in the Z direction and the B is in the Y direction. But the X direction is 0. Similarly for this point over here, now we're looking at the projection of this point into the XY plane. So our Z is 0. So we're in this plane over here, down here. And now my Z is 0. And similarly for this point, we're projecting into the XZ plane. So that's this plane over here. And now my Y, so this is my Y direction. You see it's 0 in this plane, so the Y is 0. And in general, this plane over here is the XY plane. And you define it, so it's the XY plane, and you define it when Z is equal to 0. So you just set your Z to 0. You make sure that in the Z dimension, you're 0, and then you get stuck on this plane over here, which is the XY plane. Similarly, the XZ plane over here, so that's this plane, is you get it when you set Y to be 0. So you crush this coordinate, and now you just have a plane. So that's the XZ coordinate and the YZ, sorry, the XZ plane, and the YZ plane is the plane that you get when you crush your x-axis, and you get this over here. Any questions so far? Yeah. Is this clear? Hello? Hey, guys, are there any questions? Is this clear, please? I just need a couple of people to respond.
Nope, looks good to me.
All right, perfect. I don't want to ask too many questions, and like I understand that it's annoying to watch these lectures online, but if just a few people can answer when I ask a question, that would be great, and we can move on. Okay, so now they want to tell us the formula of the distance in R3, so in 3 dimensions. So you start by having 2 points, P and Q. So right now we're in R3. So let's say we have this point over here, the point P, which will have coordinates A1, B1, and C1. And then you have another point over here in R3. Let's call it Q, and it has coordinates A2, B2, and C2. Then if you want to find the distance between them, so let's just write the distance between P and Q. Well, that's going to be, and this again comes directly from the Pythagorean theorem, you can try to first think about creating a vector going from P to Q. So try to think of the PQ vector, and then try to find its magnitude. And so the PQ vector will have A2 minus A1, and then when you're looking for its magnitude, this thing will be squared. And then you're going to have B2 minus B1 squared, and then you're going to have C2 minus C1 squared. And that will be your distance between P and Q. So it's like you're looking for the vector, and that's how you get these coordinates. And then you just square each component, add them together, and you take the square root. So, 1 second. Yeah. So, yeah, so that's what happens over here. So here you have your P, which is A1, B1, and C1, and you have your Q, which is A2, B2, C2. And now you want to find the distance from P to Q. So again, you want to look at the vector PQ. And this vector is the vector A2 minus A1, B2 minus B1, and C2 minus C1. And then you just want to find the magnitude of this vector. That gives you the distance. Okay, and over here, they just try to show how this formula works, but it's just the generalization of the Pythagorean theorem. So, yeah. So now surfaces in R3. So we can try to find the plane where x is equal to 3. So if you look at your x, y, z coordinate, the YZ plane is the plane that we get when x is equal to 0. But you don't necessarily need to set x to 0. You can set x to 3, and then you get this plane over here. And yeah, so this comes about when you set x is equal to 3. You can set x is equal to, y is equal to -5. Then you get this plane. You can just set z is equal to 10, and then you end up getting that plane. And then the two very important surfaces are the sphere and the cylinder. So let's try to understand how we get these two equations. So first, looking at the sphere in R3 centered at ABC. So if you're at 0, 0, 0, if you're at the origin and you're looking for your sphere, then with radius r, then the equation will be x squared plus y squared plus z squared is equal to your radius squared. And this is just going to be a sphere centered at the origin, so something like that. Okay, whatever. It's a sphere centered at the origin. Now, the reason that you get this equation is, again, the Pythagorean theorem. You want to find all the points x, y, and z such that they're r squared distance away from the origin. So it actually comes from the distance formula that we just wrote out, that the distance between P and Q right, is equal to the square root of a2 minus a1 squared, dot, dot, dot. And now we can consider one point on the sphere to be to come from the point P, and the second point, the origin, to be the point Q. And now if the origin is Q, then Q is equal to 0, 0, 0. And so when we're using this formula, you get x minus 0, y minus 0, z minus 0, and you set that equal to that distance that you want, and that will give you your sphere at the origin. But if you don't want just to look at the sphere at the origin, you want to put it at any point, then you're going to do x minus that point A, and y minus that point, and z minus that point is equal to r squared. So that's for the sphere. For the cylinder, let's say you want a cylinder and you want that in the z direction it goes to for infinity. So here's your cylinder. Then in two of the directions, you're gonna restrict the cylinder, which means that in the x and the y direction over here, because you have x minus a and y minus b, in the x and y direction, you're going to have circles. So if you just cut with a plane through any part of this cylinder, you're going to get little circles. And that comes from this part of the equation when you're ignoring the z direction, because if you're in R2, so let's first imagine that you're in R2. So now we're in R2, and we have something like this. This is my x and this is my y. Then how can I get a circle over here? Well, that's just x minus a squared plus, and if this is at the origin, the a is going to be 0, plus y minus b squared is equal to r squared. But then you can imagine that we just extend these circles to infinity in both directions, and we just add a coordinate. So instead of having x, y, we now have a z coordinate sticking out over here. Or a better way to draw this would be x, y, z, and then you have a cylinder over here. So that's why this gives us the equation of a cylinder. Any questions so far about the equation for circles or for cylinders?
No, it looks great. Thank you.
Okay, thanks. So let's do the following example. So first they want us to describe the set of points defined by the following conditions. So the first condition is x squared plus y squared plus z squared is equal to 4. So we already know that this equation alone gives us a sphere with radius 2 centered at the origin, because for A, B, and C, you have 0, 0, and 0. And then they tell us they want y to be positive. So that means that in the negative y direction over here, we just cut that out, and we're left with this half hemisphere in the just the x, z, y direction. So that's the answer for the first part for A. And then for B, so they just give us this. So this clearly looks like a cylinder centered at 3, 2 with radius 1. And then they want our z to be bigger than negative 1. So when you do that, you, sorry, one second. First, okay, sorry. You're going to start the cylinder at where z is bigger or equal to negative 1. So I guess that's what they're doing over here. The fact that this is centered at 3, 2, okay, that makes sense. And then it will start from negative 1 and go to infinity. Fine. Okay. And this, again, goes back to what I just mentioned. that if you have 2 points P and Q and you want to find the distance between them, or again, you can find the vector between them and find the magnitude of that vector. That will give you the distance between P and Q. And this is the equation that we saw before. Again, similar, it's very similar to the equation of the sphere, and it's fairly similar to Pythagoras's equation. And the reason for that is because it's the same thing for both. Okay, and then in 3 dimensions, we have all the same things that we had in 2 dimensions. So you can translate your vector and it will be equivalent if it has the same direction and the same length. You can think about the vector with the position at the origin, and they call that V naught, and over here it starts from the origin. Now your vector will have 3 components, A, B, and C, because we are in 3 dimensions, X, Y, and Z. We can try to find the components of the vector between P and Q. And like before, it's going to be the component of Q minus the component in P. So it's A2 minus A1, B2 minus B1, C2 minus C1. And so my vector V is going to be ABC, and that will come from A2 minus A1, B2 minus B1, C2 minus C1. And here's an example for that. Okay, and again, if you multiply by a constant, you just put the constant in. If you add your vectors, you add the components. So everything from 3 dimensions is basically the same. So now they give us 2 vectors, V and W. And first they ask us to find the magnitude of V. So the magnitude of V is going to be equal to the square root of 3 squared plus -1 squared plus 2 squared, which is going to give us 9 plus 1 plus 4, which is going to give us the square root of 14. So that's going to be the magnitude of V. Now they want us to find the unit vector in the direction of V. So if the magnitude of V is the square root of 14, then its unit vector, so EV, is going to be equal to 1 over the magnitude of V times the vector V. So it's going to be 3 over the square root of 14, and then -1 over the square root of 14. And then 2 over the square root of 14. And that's going to be our unit vector. So again, our magnitude is 14, and our unit vector is just 1 over the square root of 14 times the vector. So you can put it into the components. Okay, 6V minus half W, that should not be too complicated. And then they want to know whether these 2 vectors are parallel or not. And the answer is, if they were parallel, then there would be some number such that V is equal to that number lambda times W, right? Because let's say you have 2 vectors, and again, we're in R3 now, so here. So if they're parallel, we're in 3 dimensions, X, Y, and Z. And if you have 2 parallel vectors, it means that they share the same direction. One of them might be a little longer than the other, but at least they share the same direction, which means that if I put the tail of this vector onto the tail of this vector, it would basically line up in the same direction. And the only way for that to happen, if this is the vector V and this is the vector W, is if you have that V is equal to some number times my vector W. So does that make sense over here? Well, it doesn't really look like that. 3 going to 4 and then -1 to 6 and 2 going to -8 definitely won't be a number that if you multiply V by, you're going to get W. So they are not parallel. And then in R3, instead of just the I and J that we had before, right, we had that I before was equal to 1, 0, and J was equal to 0, 1. So now you're going to have an I, J, and K. And so again, this is my X, this is my Y, and this is my Z. The I lies in the X direction. So this over here, this is your I. And then your J lies in your Y direction. So here's your J. And then your K lies in the Z direction. So this over here is your K. And so every vector, like before, the vector A, B, C is equal to AI plus BJ plus CK, right? Because same thing we did before. We're going to have A times 1, 0, 0 plus B times 0, 1, 0 plus C times 0, 0, 1. And this over here will give you A, B, C. So that's what they show over here. A, B, C is equal to A times I plus B times J plus C times K, which is equal to AI plus BJ plus CK. And so, for example, -9, -4, and 17 can be written out like that. And over here, we have a nice picture. Here's your I, here's your J, here's your K, and any vector can be written as a certain amount of I's plus a certain amount of J's plus a certain amount of K's. And that will give you your vector. Okay, so far, any questions? Hello?
No, sense. Thank you.
Okay. So now we have curves and lines. So you can think of a vector, instead of being fixed, you can think of a vector that changes with time. So that's going to be this vector RT, which is going to be equal to XT, YT, and ZT. So now each one of these components is going to be changing with this parameter T. So as T changes, these change. So you can think when T is, let's say, 0, that you have this vector going from here to the curve. But then as T, let's say, increases with time, as T increases, this vector might be moving because you have a different vector, and it kind of traces out a curve. And if T is negative, you're going in the opposite direction. So yeah, so that's this vector over here. So instead of having a fixed vector now, we have a curve that goes through R3 and is represented by this following vector that changes in time. So that's a very simple way to define a curve. And we can also define a line this way. And I think the way, let me see, the way they're doing it now is that they have some original point, and then they take a vector. Oh, sorry. Yeah, so this is just a geometric description of a line. I'm not 100% sure how much it matters as much. Oh, okay, sorry. What they're telling us is this, that if you have P, if you have this point over here, which is going to be the point P, and you have this point over here, which is going to be the point P0, we can define a line using these points. You first look at the vector between these 2 points, and okay, or you're looking at the vector v. So you're either looking at a point and a vector v, or you're looking at 2 points and you're finding the vector v between them. Not sure how much that really matters. And then your line is going to be formed by just going to infinity with this vector over here. So let's see how to actually do that. I mean, geometrically, this is fairly straightforward, but the equation of a line is this equation over here, and it comes out from the following intuition. You have a point on the line. So let's say here is a point, and then I can take a vector v. So the point over here is the point r naught. And then you can look at the vector v pointing away from r naught, and you can find the line that goes through this vector. So you can imagine a line like this. And how do you do that? Well, you just look at r naught plus, so you can imagine this as a vector here, plus tv. So that's going to end up giving you this vector pointing at this point over here. So let me actually go to the whiteboard. Colors might be helpful. Okay, so once again, we have our x, y, z, and then we have the point over here, r naught. And so first we can think of a vector going to r naught, and then we can think of the vector v going away from r naught. And we want to find the equation of the line that continues like this forever. Now, any point on this line can be written as the vector r naught. Instead of thinking if this is a point, you take the vector r naught, and then you add to it t of v. So tv is going to be some vector. So it's going to either be, it can be this vector or a smaller vector, right? T just stretches, expands v, and also makes v go in the negative direction if t is negative. So we get all of these vectors. And then r naught plus that vector will give you all of these vectors. So this is going to be one, this is going to be another for a different t. And so we keep getting points on this line. That's a point, and this is a point. So our line over here is going to be r naught plus tv. And our r naught has x, y, and z coordinate, and our v has an x, y, and z coordinate. So in general, we will get something like that. Or in other words, our x coordinate, x of t, is going to be equal to x naught plus ta. And our y of t is going to be equal to y naught plus tb. And our z of t is going to be equal to z naught plus tb, plus tc. So that's what we have over here. X of t is equal to x naught plus at, y of t is equal to y naught plus b of t, z of t is equal to z naught plus c of t. And then t takes values from positive and negative infinity. So as t gets very positive in this type of example, we're going to go along the line, we're going to go in that direction. And as we go negative, we're going to go in that direction. Are there any questions about how to write lines?
No, it's great. Thank you.
So now here's an example. So they want to find a vector parameterization and a parametric equation. So these are the parametric equations, each one of these, the x, the y, and the t. And the other one is the vector parameterization. So they want us to find the vector parameterization. So this is in vector form because you're keeping this vector, and these are not. So they want to find the vector parameterization and the parametric equations for the line through the point P naught with the direction V is equal to 2, 1, 7. So again, our R of T is going in this case to be equal to P naught plus T and then this V over here. So that's going to be 3, -1, and 4 plus t of v over here, which is 2, 1, and 7. So that's the vector parameterization. And then if you want to put this all together, you're going to get 3 plus t2 or 2t. So okay, I'm just going to do t times 2. And then you're going to get your -1 over here plus t. So t1, t. And then you're going to get your 4 plus 7t. So that's how each one of the coordinates will look. And then if you want to get your parametric equations, you're going to get, this is your x of t, this is your y of t, and this is your z of t. So your x of t is going to be 3 plus 2t. And your y of t is going to be equal to -1 plus t. And your z of t is going to be equal to 4 plus 7t. So, yeah. Let's try another problem. Yona, can you guys go into the other? Thanks. Any questions about this example?
Nope.
Okay, so let's try the next problem. So we want to find the parametric equations of the line through 2 points. So in order to do this problem, we have to first find the vector. We can use any one of these points as the initial point, as the P0. But then we can find the vector between these points, and then we can use that as the vector. And should I do this problem, or is this understood and we can move on?
I learned by examples, so seeing another worked out example would be great.
Okay, perfect. So let's do that. So, 1 second. Okay. So we have the point P and we have the point Q. So first we want to find the vector PQ. So here's our vector. So the first coordinate is going to be 2 minus 1. And then the second coordinate is going to be 5 minus 0. And then the third coordinate is going to be -1 minus 2. So what we get in the end is 1, 5, and -3. And this is going to be our vector v. So what we're doing over here, essentially, is, okay. So, sorry. Oh, okay, I did not mean to do that. And okay, sorry about that. So the points are 1, 0, 2, and 2, 5, -1. 1, 0, 2, and 2, 5. So here is my x, y, and z coordinate. And here's, let's say, my P. And here, let's say, is my Q. And I want to find the line that goes between these 2 points. So the way to do this is, so again, any equation for any line is going to be, you want to find one point on the line, and we call that point, let's say, R0. So let's choose this point to be our R0. So the point P is equal to R0 for 1 second. And then we want to find a vector on that line. And then that vector will be the vector V. And then the equation of the line is going to be, so let's call the line R of t. It's going to be R0 plus TV. So I already know my P, so I just need to find my V. And I can find my V by looking at the vector from P to Q. So the vector from P to Q is going to be equal to, so like we said, 2 minus 1, so that's 1, and 5 minus 0, and negative 1 minus 2. So that's negative 3. So this is going to be my vector V. And so now the equation for my line is going to be my P. So that is 1, 0, 2, plus T of my V. This is my V. So that's 1, 5, and negative 3. Or in other words, you can simplify this. So this is going to be equal to 1 plus T, and then 0, and then you're going to have 5T, and then you're going to have 2 minus 3T. Or in other words, for your x coordinate, so x of t is going to be 1 plus t, and your y coordinate is going to be 5t, and your z coordinate is going to be 2 minus 3t. Okay. Fine. So what is this example? Show that this and that parameterize the same line. So over here, they give us two different lines, and they want us to show that the two lines are the same. So first, what you need is you need this vector and this vector to be going in the same direction. So you would need them to be parallel. And they are. If you take negative 2 times this vector, so you're going to get 4, you're going to get negative 1, and you're going to get negative 6. So negative 2 and negative 6. So these vectors definitely are going in the same direction. So now the only thing that you need to show is that this point lies on this line, right? And that this point over here lies on this line. Why is that? So let's say I have two parameterizations. So yeah, let's say I have two parameterizations. R of t is equal to R naught plus TV, and so this is R1, and R2 of t is going to be equal to R prime naught plus TV prime. So first, if these two parameterizations describe the same line, so you can think about these two lines. You have one line where you have R naught, and then you have this vector V, and here's that vector, and it parameterizes the following line. So that's my line. Now, if this line parameterizes, if this equation parameterizes the same exact line, then my V prime has to lie on this line. So my V prime is going to, let's say, not lie on the line, but at least be parallel with the line. So this, let's say, is going to be my V prime over here. And this over here is my V. So if this is my V prime and it lies on the line, then, and it's parallel to V, then the only last thing that I need to know is that this point over here, this point over here, this is R not prime, also lies on the line. And if I have those two facts, I'll know that they parameterize the same line. So we already showed in this case. So over here we have this V. So V is equal to -2, 1, and 3. And V prime is equal to 4, -2, and -6. So if you look at -2V, you're going to get V prime. So they are parallel. So that's fine. So now this over here, this point, my R naught is equal to 1, 1, 0. And my R naught prime is equal to -3, 3, and 6. So first, does this point lie on this line over here? Well, if I take this t to be equal to 1, then I'm going to get -3 plus 4, which is 1. And I am going to get 3 minus 2, and that's going to get me to 1. And I am going to get 6 minus 6, and that will get me to 0. So check, this point lies on this line. And that actually is all we need to know. In order to find whether this point lies on this line, we only have to take t to be, my guess is to be 2. And then we're going to have 1 minus 4, and that will get us to -3. And we're going to have 1 plus 2, and that will get us to 3. And we're going to have 0 plus 3 plus 6, and that will get us to 6. So yeah, these two equations parameterize the same line. Any questions about that? Okay, so another thing that we can do is we can determine whether two lines intersect, and we can also figure out where they intersect. If they do intersect, then you can set them equal to each other. Wherever it is that they intersect, you're going to have that R1 of t is equal to R2 of t, right? So that's exactly what they do over here. This over here is R1, and this over here is R2. And then for the x coordinate, in order for the x coordinate to intersect, you need that the x part, 1 plus t1 times 3 over here, should be equal to the x coordinate over here. So that's 3 plus t2 times 4. So 3 plus 4 times t2. So this is the x coordinate. And then you want the y coordinates to be related. So you want your 0 plus your t1 times 3. So that will be 3t1. You want that to be equal to the y component over here, which is your 6 minus 2 times t2. And then you want your z component to be equal as well. Okay, and so then you can solve the equations. And so let's see how they do it. So they first say, let's solve the first two equations for t1 and t2. So forget about this and try to solve these two equations, because we have two equations and we have two unknowns. So we can find t1 and t2. And okay, that's just the normal way of solving two equations, subtracting the second equation from the first. We get that 1 is equal to 6 times t2 minus 3. So they are subtracting the first equation they're subtracting this from this, So the 3t1 and the 3t1 cancel. So you get that 1. So that's the one over here is going to be equal to this 3 minus. So let's try to actually do this. Sorry. 1 second. Okay. Here. So we have that, sorry, 1 plus 3t1 is equal to 3 plus 4t2. Okay, and then from the second equation, we have that 3t1 is going to be equal to 6 minus 2t2. So now if we subtract the second equation from the first equation, we're going to get that 1 over here, so 1. And then the 3t1 subtracts the 3t1. And then we are going to have 3 minus 6. So this is going to be equal to 3 minus 6, which is negative 3. And then we're going to have 4 minus 2, which is 6. So plus 6t2. So that's what we're going to end up having. So now solving for t2. So this is going to give us 4. And you're going to have 4 divided by 6. So t2 is going to be 2 over 3. Okay, so now that we know what t2 is, we can figure out what t1 is by subtracting t2 into this equation, for example. And they do that for us, and they tell us that t1 is equal to 14 over 9. So right now we have t1 is 14 over 9, t2 is 2 over 3. And at this point, we have that R1 and R2 have the same X and Y coordinates because that we were setting the X, we were going to set this, we were using this equation and this equation to find T1 and T2. But if you now plug in the T1 and the T2 that we found into the Z coordinates, so if you plug it in into this, into this equation right over here, you will get that the two signs don't equal each other for the T1 and the T2 that we discovered. And so the Z coordinate they will not share the same Z coordinates. So they will not satisfy the third equation. And so therefore there is no solution and the lines don't intersect. And here's a nice picture for that. So next time, I think we'll start with this summary and we'll continue from there. Are there any questions?
Yo, how'd you get from the 1 plus 3t1 equals 3 plus 4t2 to the next line right below it? The 3t1 equals 6 minus 2t2.
So here, I'm just taking the two equations. So this just comes from this equation. So the 3t1 is equal to 6 minus 2t2. So 3t1 is equal to 6 minus 2t2. And then this equation gave me this line, 1 plus t1 is equal to 3 plus 4t2. So 1 plus 3t1 is equal to 3 plus 4t2. And then you subtract this equation, you subtract this from this to solve for your t1 and your t2. So your 3t1 and your 3t1 cancel, and you get 1. So did that answer the question?
Yeah, that's perfect. Thank you.
Yeah, so this y coordinate over here, you want the x, the y, and the z coordinate for these two equations to be the same. So you set the x coordinates the same, and the y, so that's the x coordinates, the y coordinates, and the z coordinates. Fine, I'll redo this problem next time, and we'll continue from there. Any other questions?
I have a question. Is Monday's lecture, the recording, going to be posted on Canvas?
I don't think I have the recording from Monday. Like it didn't record it correctly. It's like
Okay.
second or- so I don't think so, but I'll try to put this recording on Canvas. Yeah.
That's fine. Thank you.
Anything else?
Can you explain how you found the value of T1 again? Did you just use the equation from the y equals and then plug everything in? Or
Yeah, so I'm
I'd
gonna
go
fine.
behind
So for this problem, I'm gonna try to redo this problem on Tuesday. I'm going to redo this problem. Okay.
thank you.
All right. Anything else?
Do we have homework that's due soon?
Yes, you have homework that's due on the 28th.
Okay, thank you.
Anything else? Okay, thank you very much. And yeah, if you have any questions or you want to meet to work on problems, please let me know and have a nice day. Okay.